Hi guys. So what I want to do this evening, or just the morning for you, is to kind of give you an overview of kind of what it is that we're going to be studying before we get into the technical details of it. And I should also say that part of the reason why I'm doing this with Mathematica is that somehow in the course of my research today, I seem to have misplaced my iPad pen. So instead you get to see my face. And I'm going to walk you through some things that are related to the ideas that we've been talking about. And so we're going to be looking at what dynamics looks like in action. And then I'm going to talk about how slight changes can drastically change behavior. And then we'll talk a little bit about how this links up with the rotor notes. And I will give you this Mathematica notebook that you can play around with as well. So with that said, let's pull up Mathematica. Okay, so I'm calling this the complex visualizer. So there'll be a second version of this that goes up in the notebook. So when we're looking at complex dynamics, one thing that we can do is we can ask, okay, given a function z squared plus c. So this first function that I'm looking at here is the function, let's see if I can not go late like that. This is this first function we're looking at is f of z is equal to z squared plus c, where the c value is given right here. This is 0.18 plus 0.54i. It's totally okay to have a c value that looks like that. And then I've sampled a starting point. So the starting point I've chosen here is minus 0.75 and minus 0.918. You can see that this dot down here is the dot that we're looking at, this dot down here close to -1. And then if I actually construct this thing and I let Mathematica calculate the path that that object takes as I repeatedly apply the function f of z to it, we can see that it looks like the path of the object taking is it's spiraling into a single point. So this is a sort of an animated illustration of what a fixed point looks like, what the behavior near a fixed point looks like. And to a large degree, these things are going to be stable around the fixed point. So as long as we stay close to the fixed point, so if I change this slightly, maybe I can put a 0.175 right here, we might see a slight change in the path that we're taking. But you can see that we still end up sort of pulled into the same fixed point. Now, more disturbingly is that with very small changes, we can end up not getting close to the fixed point. So if instead of being 0.9 minus 0.9i, if I change the initial value that I've put in to say 1.2, we can start seeing more and more chaotic behavior as we go away. So even here, just with 1.2 in the I component with the same input, we have non-convergent behavior. The reason that the graph disappeared is because the f is like sending these points skyrocketing away to infinity. And you can see as we come with just little tiny changes, as we come closer and closer to the original set, the behavior stays chaotic and it stays chaotic. And then at some point we'll cross a threshold where once again, we have convergence to the fixed point. So very small changes in the location of that initial point correspond to very different behaviors in the long-term behavior of the system. So of course, it's not just the case that functions can have single fixed points. It's also possible that we can have plots where we have behavior that looks like this. So here's an example of an evolution. So I'm calculating the orbit of a path here. And for all the world, it looks like this function is falling into a pattern where it's on this triangle, and then it's just going to repeat the sides of that triangle over and over and over again. And if we'd like to check to see if it's really trapped in the triangle, or if instead what's going to happen is it will be sucked into some sort of fixed point in the long term, we could actually extend the number of points we calculate this thing on, or run the same calculation. And if it's stable, what we should see happening is that that triangle stabilizes itself. And so you can see that the path sits on top of itself over and over again. And this is what we might describe as an orbit of period 3. That is, the points are being attracted to a set of 3 points, and those 3 points are repeatedly being sent to each other. So we can have one fixed point, so that's like an orbit of length 1. We can have an orbit of length 3. Here's an example of an orbit of length 2. We've already seen this example before. And you should be able to see here that in the middle that point is just whipping back and forth like between 0 and -1. We calculated this one. This is the function z squared minus 1. You know it's z squared minus 1 because the c value that we've chosen right here is what dictates that. Likewise, you can tell, just like in the earlier cases, it's very easy to choose points that break this. If I start sliding away from the origin, I'm going to get different paths, and even just a change of adding just 0.2 to that initial value destroyed the convergence of this thing. If I come into 0.1, I still diverge. If I'm at 0.01, that is close enough to make this convergence happen. So again, very, very delicate behavior. This is kind of why we talk about these things as being chaotic. Chaotic systems are systems that are very, very responsive to the initial conditions of the system. Okay. So here's a fun one. So this is an example. I'm not about to see that yet. Here's an example where my c value for z squared plus c is -0.5 and 5.75i. And this is an orbit that has periodic behavior that looks like a period of 5, which is to say, as the points are going around and around, they're being attracted into a subset of 5 points that they're being pulled into each other. So as this orbit evolves, we find that we're landing on the same 5 points over and over and over again. So we would call this an attractive orbit of period 5 because it pulls things in. So the big question that we need to answer is, why is this, what's actually going on here? Why is it the case that, if it's the case that locally, so near one of these points, things are pulled into one of these orbits, and away from it, they're pushed away, is there a way that we can visualize or calculate the set on which points converge versus where points don't converge? And it might surprise you to see that these sets are actually quite complicated. So your first impulse might be to think that they're circles, because circles are the natural candidate for things being pulled in or pushed away. And even if you look locally, I mean, there are small circles around these attracting orbits or attracting fixed points where points close to those circles are pulled in. But the boundary of the set, the boundary between the set where points act well and the set where points act badly is actually pretty complicated. So in Mathematica, we can visualize that with a command called Julia set plot. I'm going to go through the mathematics of how to construct these things in a future video. And I'm also going to go into the technical definitions of things like attracting orbit and how you detect if an orbit is attracting or not. But for now, again, this is sort of our orientation to what we're pushing into trying to understand here. So suppose that I wanted to look at the Julia set for one of these plots. So you can see in this first plot here, this blue set that traces the edge, that is the boundary between points that are attracted and points that are going to run away to infinity. So points that have bounded behavior lie on one side of that very complicated set, and points that run away towards infinity are on the other side. If we run this animation, what we'll find is that same orbit that we started with, where we're being pulled into an attractive fixed point. And the reason that that happened is because the original point that we chose is on the interior of this complicated boundary. And as I slide that point out towards the edge of the boundary, things converge slower, perhaps. And if I go over the boundary, well, now I'm not in what's called the basin of attraction anymore. So I'm not being attracted, I'm outside the set that can be pulled into that fixed point. And so we can visualize that by just picking a different z naught and running the same visualization. The Julia set, that is the blue boundary between where things are attracted and where things repelled, that's a function of the value c, because z squared plus c is just the function. What we're changing is not the boundary between where things are attracted and where they're repelled, but where we're picking our initial point to study. So let's run this again, but let's pick a point that's outside of that range. I think we can do that as simply as like putting a 2 out here. So you'll notice once this renders that that point is just on the outside of the basin of attraction. And because it's just outside that boundary, it cannot converge. In fact, the reason the plot disappears is because the numbers get so close to machine precision on the huge side that Mathematica just refuses to plot them. So this is divergent because that initial condition is on the wrong side of the boundary. And if we slide it back inside the boundary again, what we should find is that we get a convergent series again, or a convergent behavior again. And you can see that now our initial point is back on the correct side or attractive side of the boundary. We are once again in the basin of attraction. And so our long-term behavior is going to be pulled into the fixed point. Now, these can be amusingly more complicated than we're looking at here. So there's going to be some structure that we're going to be looking at. This is what it looks like. The Julia set, the rather interesting looking Julia set. But you've probably even seen these pictures before. So every time you've seen one of these sort of fractally pictures, essentially what you're looking at is the boundary between where some function is well behaved and where it's badly behaved. So with this picture, what we've done is we've picked an initial point way out here on the edge, and then it's climbing in to the set. And then notice that it's falling into this sort of triangular pattern where it's bouncing back and forth, not just in sort of random triangle, but the points that it's landing on are each contained in one of these weird little blobby segments. One thing to think about would be, as it crawled from where it started to where it ended, are the sets that it's landing in, sort of these fractally looking sets, are they consistent? Is there some sort of association between the different bulbs of this Julia set that we're looking at? Okay. And once again, there's some sort of mathematics that goes into detecting how you know that this particular object has a period of 3. This is going to be an attractive orbit of period 3, which is part of another part of what we're going to study going forward. We'll do a couple more of these. This is the set, the Julia set. This is the Julia set for the function z squared minus 1. You can see here once again that it's very easy once you get outside of these sort of main areas. But if you pick a point that's outside of those, you have divergent behavior. This one is harder to see what's happening, but the function is essentially bouncing back and forth between 0 and minus 1. You can just directly compute that. And for our star-shaped region, apparently I have not set this up correctly. So let's try that again, shall we? What did I break here? It's all right. It's all right. Add code. Okay. So now you can even see the fact that these sort of things are spread out in these fingers. And once again, we're starting with an initial point that's inside the, I would call this the inside. And it's being thrown not into the sort of region that it started in, but to some other region in the interior. And it's pretty easy to see that these 5 regions that are sort of this maple leaf looking collection around that central point are going to be the set that constitutes the place where that attractive orbit is going to happen. So we're sort of left with some questions. And one of the questions is, how did I know that this is what these things were going to do? How did I know how to choose the different examples that I picked here? And what's the sort of overview of the mathematics that we're going to be looking at more computationally that are driving what's going on behind the scene? So remember, when we're doing this, all we're really doing here, I might as well turn this back on again because it's fun. All we're really doing here when we're doing this is taking the function f of z squared plus z and applying it to this initial point z naught. And then we're taking that output and putting back in the function and taking that output and putting back in the function. So this is an iterative process. How did I know where this structure was going to come from? So the answer is, it turns out to be the case that you can look at something called I guess I'll let the cat out of the bag here. There's this object called the Mandelbrot set. And there's a relationship between the Mandelbrot set, which is about the plus c that sits on the function, and the Julia set, which describes which input values will converge. So I'll share as the last part of my orientation here. I'll show you what it looks like when you calculate these things. So this is a problem called, or a software called Mandel, which is a Mandelbrot set generator. And I will reset it so that we can see what's going on. Not do that. Okay, so this is the Mandelbrot set. What the Mandelbrot set on the left-hand side is doing is telling you, it's a map that tells you all of the different c values that you can put into z squared plus c that make interesting or convergent Julia sets, connected Julia sets. That is the boundaries that we have a good boundary between where things are attractive and where things are repelling. So if I pick a dot in here, what it tells me is, okay, for that particular dot, we have a z squared plus c, and then the picture on the right is calculating that same boundary. So if I go to a point that looks like -5 and 0.75, I can find Julia sets that look exactly like the set we were computing that had the period of, or the orbit of period 5. So I want you to connect here. What I've chosen on the left-hand side is a c value that goes into z squared plus c. And notice I cheated actually, because this particular calculator tells you the period associated with that particular bolt. So every c value in this little ball, corresponds to one of those boundary sets where there's going to be an orbit of period 5 for every one of these. And it's a fascinating question to ask how I know that's the case. And that's going to be the content of some more direct calculation that we'll do for the next lesson. You might ask, okay, well, what happens if I click into another one of these little balls? Do I get different periods? And that's a good question. So if you click somewhere else, you might find, oh, look, the period 7. These are, every c value in here gives you a z squared plus c that gives you period 7. And so on. So you come down the chain, here's what the period 9s look like, and you can keep doing this calculation. What you're seeing on the right-hand side is the boundary between the points that converge to that orbit and the points that get thrown away to infinity. So the further out towards the edge, the weirder the c values that you put into z squared plus c, the less stable your iterative behavior actually is. And actually the white dots here, I don't know if you can see those, but if I cover to this side of the graph and I zoom in on these dots, let me do it. You can see here that these little white points, those are supposed to be the points that collect the convergent orbit or the attractive orbit. Now you might ask, okay, so we talk about fractals. What does fractal mean? So fractal refers to what's called self-replication in these sets. And one thing you might notice is that if you look on the left-hand set, Mandelbrot set, that the ball that's up here on the top looks an awful lot like the one that's stuck to the side here. And if you zoomed in on the one stuck on the side, you might notice that the balls that are stuck to the outside of it also look like itself. And so you could zoom in on that, and you get these sort of self-replicating structures on the side. Things get a lot more complicated when you're zooming in here. So yeah, that's basically the picture, is that what we're doing when we're looking at this, what we're going to be doing is that we want, let's back up so I can remember these. What we want here, what we want to consider is the relationship between the parameter that we put into the z² plus c, which is over here, and the set of attractive, and this attractive set on the other side. And so this is called the Mandelbrot set, and this basin of attraction for the particular z² plus c is called the Julia set, is the boundary between these two things. And I guess just for the end, what I can do is I can compare these side by side, so you can see that I'm not just making this up, that these are really they're both the same thing. So you'll notice here that on the Mathematica program, I have a C value of minus 0.5 and plus 0.575i. If I come up close to that here, you'll see that the sort of Julia set that I get out looks an awful lot like the set that Mathematica produced. So choosing the C value on the left to be equal to something pretty close to what I chose gives me the Julia set on the right that tells me where the points that can converge in iteration live. If you scroll back up through the rest of this, of C value of -1 is in this circle. So we can go in here and you can see that that is pretty much precisely what what that set looks like. If we scroll up here and I look at a C value of -0.1 and 0.75i, so -0.1 and 0.75i is going to be up in here. We get that sort of behavior, and so on and so forth. And essentially, once I knew what was going to happen, I just put it into Mathematica and took a look at it. I will say that our initial study is going to be primarily focused on functions of the form z² plus c, but we spent a lot of time in the class talking about linear fractional transforms, and there is another set of dynamics associated with linear fractional transforms. So if you go to rational maps, you can go and look at your favorite class of rational maps. So let's see, there's my rational maps here. Any good ones? One is a cute one. Some pretty strange sets running around in the world associated with these things. So anyway, all right. So this stuff that we've talked about today, let's put this back on something reasonable here. The stuff that we've talked about today essentially corresponds to in the rotor notes. You should notice that this is basically covered in the section that starts here. The Mandelbrot set from the inside out, that starts on page 20. We've already been through almost a quarter and a half of complex analysis. You do not need to do anything that came in that complex analysis review. You know all those theorems except maybe Montel's theorem. What I'd like you to do next, I'd like you to read your way through the technical definitions of attracting periodic orbits. I'd like you to look at what it means to be a multiplier, and then how to compute a multiplier, and then the definitions of basins of attraction. And then you'll see that in Rotor's notes, he actually then immediately goes to pictures of these basins of attraction. Okay, so I will post this video. I will post this notebook. I encourage you to play around with this stuff. And if you want to take a look at a really important theorem and think about what it means, you should look at Kroenig's theorem here. So Kroenig's theorem is what actually tells you that what's going on is that locally these maps actually behave linearly. And I don't know if you noticed or not, but there's conformal maps involved in that. All right. So I will post this. I will talk to you guys soon, hopefully. And yeah, I hope you're enjoying following this. See you soon.